Hello, this is Janik Barmi here, and this is the third video in the series on ship or body stability. First, let me review what we done in the previous two videos. We talked about the stability of cylinder, and the cylinder have a dome shape of stability, which the x-coordinate is the density ratio. It's the density of the solid or the floating body relative to the density of the liquid versus the radius times the draft, which is the height of the cylinder, like that. This is the height and this is the radius. And the maximum that we can see here, it's about 0.66. You notice that this graph is made in non-dimensional form, so we can use it on any kind of shape or any kind of geometry, and we can get it pretty much correct. What I want to talk today is about the shape which is rectangular or extruded rectangular. It's like some kind of rectangular shape, and it's extruded. It's like very long, and we can treat it as two-dimensional shape. If we have a solid and we put it on a solid surface, and we can see that the amount of angle that it can have, it's 6 angle that it will be stable, or 6 position that will be stable, and it's pretty much our experience tell us that it will be like that. It will not be like that because it will go either that way or it will go to the other side, it will go to the other side, to the other surface. In the water, we know that it's not going to happen like this, and we're going to demonstrate it. The first thing that we're going to show is the shape that is two-dimensional. In fact, this is the shape of Ever Given. It's the ship that's stuck in the Suez Canal. The ratio of the ship is 60 by 60 meter with 400 meter long, and it's a box like that with some kind of shaving a little bit on the edges. And if we were to put that ship in the water, it's unstable. And the reason that it's unstable, because that's the way how it is. We have to make it wider. So how the ship stays stable is because they load the ship on the bottom with all kind of heavy weight to reduce the gravity center. So in ratio 1 to 1, we see that it's unstable. And if we move it to ratio of 1.1 to 1.2, it's a little bit stable, have already the tilting, and we can calculate the angle that it's not stable. And if it's become 1 to 1.5, it's already stable. And if you move it, it will return to the original position that it's stable. Again, we're using the word stable, that all of these 4 positions are stable, but not in the vertical angle that we will like to have it. It's like we were looking for solid surface, that we put solid object on solid surface, we saw the specific thing. And if it's 1 to 1.2, it's very, very stable. And you can see and the ratio. This material that I'm using is a cedar wood on water, which is about density about close to 0.6. So that's unstable. If we take again a body that is 1.1 that we saw in the wood that it's unstable, and we take it from foam, which is very, very light, which is about 0.05, and we put it on that, it's very stable. If we move it, it doesn't move away. In fact, we can go even wider. You can notice that this is very narrow and this is very large, as you can see it from, move it like that, you can see it like that. And if you put it, it's about 0.089 and it's stable. The same thing if you go to 1 to 0.0789, it's still stable. And if you go to 1.6, it's still it's already less stable. It's on borderline, but it is stable. And if I will go to narrow shape like that, it will fail. It's unstable. So it has to be very narrow and long to make it unstable. That's about 1.03 or 1.4 roughly. So what we learn from this thing? We learn that the stability of almost the entire fleet of container ships that sailing today in the ocean are unstable, and therefore they have to make them very, very heavy on the bottom. That's what makes them excessively carry heavy load. In theory, unnecessary to float around and keep it in instability. Keep the vessel stable just to prevent drowning. The other thing that we want to show is the effect. This was the stability of the cylindrical thing. In that case, the maximum was 0.6, but if you go to a stability of a rectangle extruded, we can get almost to 1.2. That means rectangle shape is basically more stable than cylindrical. I hope you enjoyed this demonstration of the thing. In the next video, we will be discussing a bit about the theory that I developed in regard to this stability, and we'll explain how we got this graph. These graphs are correct for certain kind of geometry. It's what I call typical graph. They are not the only shape that is available. There are weird shapes that we have cone, and then we get really different shape that it is like that, and we will discuss it later on. Please click like if you enjoyed the video, and subscribe to the video. Thank you.